In this video, we're going to talk just a little bit about how to get semi-partial correlations and what that tells you about the importance of your regressors. Now, we're not going to go deep into the interpretation of semi-partial correlations. We'll do that in class. But just for now, this is how to get them in R and briefly how to look at them. So we have the salaries data set up right now, which we have looked at before, which tells us the salaries of a variety of individuals at a particular university or college, and some other factors about them, such as their sex, how many years they've been at the college, how many years since they earned their PhD, what kind of discipline they're in, and so forth. I'm actually going to create a R script here just so that we can see the commands as we build them. And I'm going to, I already have the car and car data package loaded. And so we're talking about semi-partial correlations, which are often referred to as SRs. And then a little bit later, we will talk about squared semi-partial correlations, which would be SR, and then a superscript, which you can't really do in code, but I'm just going to put the two there. Okay. So we're going to focus today only on the continuous variables. So we're going to see how much the years since PhD and years of service might sort of relate to salary. So let's get a correlation matrix of those things. So this is the salaries data set, but if we do just this, it's going to freak out at us because not all of these are numeric variables, but these three are. So we're going to ask just for the correlations among variables 3, 4, and 6. So we've done this trick before, where we indicate which variables we want. So if we run that, we can see that years since PhD and years of service are highly correlated. So the longer it's been since you had your PhD, the more in general you've been at the college. That makes sense. And that both of these things, years since PhD and years of service, are positively related to your salary. So the longer you've been in academia, the more you earn, and the longer you've been at the college, the more you earn. Both of those make sense as well. This is a little bit stronger. Neither of these are super strong, but they're not weak either. Okay, so let's start with a simple linear regression. We'll try to predict salary from years since PhD. So we'll just call this model 1 and create a linear model where we're predicting salary as a function of years since PhD. So salary is our Y variable, our outcome, and years since PhD is our X variable, our regressor. We need to add in data equals salaries. So when we run that, we create the model. Now we have to use the capital S function to look at the results. So we see that there is a significant prediction that we're doing. Years since PhD is valuable as an estimator of somebody's salary. And you can tell that from the very, very low p-value, the 3 decimals here. And our R squared is, I'm just going to make a note of that, our R squared is 0.1758, just a note. Okay, now let's do a multiple regression where we add in, just going to cut and paste this here. We're adding in years of service. So now the only thing that we've done is we've added a second regressor. So now this is Y, this is X1, this is X2. And we're going to call this mod 2. So you can see I just cut and pasted to make my life a little bit easier here. Now I'm going to run this We can see that we now have a second model here, and we'll look at the results here. Now, both of these regressors are significant. That means that each one is contributing uniquely on top of the other one. And based on the sign, we can see that holding years of service constant, if you have two people who've been at the college the same amount of time, but one person has been out in academia for one more year, they've had their PhD a year earlier, on average, we would expect them to earn about $1,500 more than the person who's 1 year newer. On the other hand, holding years since PhD constant, if you have two people at the college who got their PhD in the same year, but one of them's been at the college for 1 year longer, we kind of interestingly expect them to earn $629 less on average. But that is significant. So we can see how weird things can kind of happen when we include multiple variables at the same time. You might not have expected this negative sign here for years of service. But holding amount of times with your PhD in hand constant, more service actually seems to, a longer tenure at the college actually seems to be negatively related to salary. And we'd have to think about why that might be. Anyway, they're both significant, but what we might want to do is compare these to see which one is doing a more important job of estimating the outcome in terms of salary. Now, in this case, we can kind of get a sense for that a little bit, because it turns out, now we've said many times in this class, you can't compare these partial regression weights, these partial regression coefficients, because they depend upon the scale of the x and the y variables. But in this case, the scale is actually the same. So you could technically compare these and say, well, this is the larger number ignoring sign, so years since PhD is probably the more important variable, probably contributes more uniquely to the contribution of the scores, the variance in salary. But most of the time, you're not going to be able to do that because your regressors won't be on the same scale. So it's not a good habit to get into. Squared semi-partial. I don't know what just happened here. I didn't mean to do that. So before we get into squared semi-partial correlations, let's just jot down. We can see that the R squared did go up. So I'm going to make a note about that. And this is an increase. I already did the math just to see how much higher this is from this. This is an increase in R squared from the simple linear regression to the multiple linear regression, 0.00125. So not a lot, but it did go up from about 17.5% to almost 19%. Okay, so one of the best ways, we've already talked a little bit about how you can get like a quote unquote standardized regression weight, and a lot of people use those. Sometimes they're referred to as standardized regression are bad. We talked about how they're not good for relative importance. They will sometimes give you the wrong idea about which one's more important. Sometimes these are called betas, so just be aware that they are out there. You're going to run into them when you look at research. So we're not going to use a standardized regression weight for looking at the relative importance of these two regressors. Instead, we're going to use a semi-partial correlation. And a semi-partial correlation essentially is a correlation between one of your x variables and y after accounting for the overlap between the regressors. Again, we're not going to get any deeper into it than that. In class, we will explain that in more detail. But basically, you're accounting for all the other regressors and seeing in terms of how much they overlap with the one that you're interested in. And then you'll see how much correlation is left between the one you're interested in, what's left over of that regressor, and the outcome, which in this case is salary. So So we are going to use a different package in order to get this. So we're going to use the JTools package. And I actually already do have this installed and loaded. I believe it's loaded. I will try. I'll reload it. Now you can see that it's loaded because of the check mark. But again, you can use the library function if you wanted to. Already done that. Okay. So JTools, because the S function doesn't have a way, as far as I know, to give you these partial correlations, semi-partial correlations, then we have to use this other JTools package in order to do that. Just so that you know, another name for semi-partial correlation is part correlation. It's very confusing. But just so that you know, because that's what's going to show up in the output. So if you ever see part correlation, that's the same thing as semi-partial. So the function that we're going to use is called sum. So it's a little bit like the S function that we have been using from car. And we just do S mod 2. And it's going to give us a lot of the similar information. It's just organized slightly differently. But we are going to add in part core equals true. And that's going to not only give us the basic results, but also our semi-partial correlations. Okay, so I'm going to run this. Okay, what went wrong? Smod 2. Oh, I didn't call it smod 2. I just called it mod 2. Sorry about that. Okay, there we go. Okay, so here's the output from the same multiple linear regression that we did here, but now using the sum function from JTools and asking for the part correlations. So you can see a lot of this is the same. It tells us that salary is our dependent or Y variable. It actually gives us a nice sort of F statement already pulled out, gives us the R square, and it also gives us the adjusted R square, even though we didn't ask for it. So that's pretty cool. One of the things that, so I like this formatting actually, but one thing that I don't like about it is that the p-values only go to 2 decimals, and in APA format, we're supposed to report them to 3 decimals. So I wouldn't sort of completely switch over to sum, but for the purposes of getting our part or semi-partial correlations, this is how we're going to get it. And remember, the main goal here with our part correlations or semi-partial correlations is to be able to compare these two regressors to see which one is more important in terms of how much they're uniquely contributing to the prediction of salary. And so here are the two part or semi-partial correlations. We're going to ignore this for now. There's another thing called a partial correlation, not semi-partial or part. That's here. I know, super confusing. But we're going to compare these for magnitude. So we're going to ignore the sign and see which one is further away from 0, which one is closer to 1 or -1. And we can see that years since PhD is larger than years of service. So this is the more important one in terms of uniquely contributing to the prediction of salary. How long it's been since you had your PhD is more important controlling for years of service than years of services controlling for years since PhD. So we have our semi-partial correlation for years since PhD is 0.28, and I'm going to just make that a comment, and then our semi-partial for years of service is -0.11. Now, just to let you know that sometimes if you wanted this to be in like proportion of variance, like we have R squares, the proportion of variance accounted for by all of our variables, So it was 0.1758 when we just had years since PhD, and then it went up to 0.1883 when we added in years of service. So together, these two are telling us that we're explaining about 19% of the variability in salary by knowing these two pieces of information. And that's this much higher than it was just from this one piece of information. Sometimes people will report squared semi-partial correlations. Now, this sum function doesn't square them for us, but we can do that if we want. So, for example, if we square these two here, I'm going to get out my calculator. Let's see. So SR squared for years since PhD is 0.078, and SR squared for years of service is 0.0121 or 12, something like that. So you could square these things, and then it would be considered the proportion of variance that one variable is adding on top of the other. Now this is actually, if we look at this 0.012, the squared semi-partial correlation for years of service, this is actually the same thing as the increase in R squared that you get from adding that variable in. So there is that link there, that if you take any number of regressors and you add one more, the semi-partial correlation you get for that final regressor, once you square it, is equal to the increase in R squared that you get from including that variable. So just a note that there's a connection point there. Either way, you can look at the regular semi-partial correlations or the squared semi-partial correlations, and the larger of them is the most important for contributing uniquely to the estimation of your outcome. Again, we'll get into this more in class, but this is how you would use R to actually get those values. And then you can just kind of compare them to see which one is contributing more uniquely than the others.